Hello, my name is Brett Frazer. I am an Assistant Director in the Data Linking Methodology section of the Methodology Division at the Australian Bureau of Statistics. This talk will cover the person linkage spine, what it is, how we built it, and how we are maintaining this spine over time. The ABS has developed the person linkage spine, or the spine, to efficiently and effectively combine person-centred administrative and survey data sets to create a comprehensive picture of Australia over time. As there is no single unique identifier for Australians across government datasets, Commonwealth and state data must be brought together using data integration methods. The ABS has developed the spine as an enduring piece of data linking infrastructure that is the core of the multi-agency data integration project data asset. The spine aims to broadly cover all people who are residents in Australia from 2006 onwards by integrating information from three core datasets: Medicare data, Social Security data, and tax data. The first production spine was created by the ABS in 2018 and included persons who are active in any of the three core datasets. One important enabling feature of the core datasets is that they contain what we call event-based data. This means that they contain information for people across the entire reference period. For example, name and address changes are included, so if a person has lived in 5 different addresses across the reference period, we obtain details of all 5 addresses, and this information can be used to improve the quality of linkages done both for building the spine and also linkages to the spine. The three core datasets were linked together using a deterministic methodology to form clusters of IDs. First, the Social Security data was linked to the Medicare data, and then the tax data was linked to the combined Medicare and Social Security data. Each resultant cluster is called a spine element. The resultant spine aims to contain all unique individuals across the three core datasets, so that one spine element or cluster corresponds to one unique individual. Several types of elements are possible. Where an individual appears on multiple datasets and can be linked, their IDs from each of those datasets are contained within the one spine element. Where an individual appears on only one dataset, they still have a corresponding spine element which contains only their ID from that dataset. Where IDs have been identified as duplicates, the element they form can have multiple IDs from the same dataset. The spine itself is just a list of elements and the dataset IDs that each element contains. One key enabling feature of the event-based spine is that it allows any other person-level dataset linked to the spine to effectively be indirectly linked to each other. So, if person X from dataset A and person Y from dataset B have been linked to person Z on the spine, we can assign a link between person X and person Y without doing a direct linkage project. This makes linkage more efficient as each dataset only needs to be linked once and can then be assembled in a product with any other dataset linked to the spine. The longitudinal nature of the spine also provides the benefit that two datasets with different reference periods can still be indirectly linked to each other as long as their reference periods overlap the scope of the spine. In this example, though datasets A, B and C have no overlapping reference periods, they can each be linked to the spine and then indirectly linked to each other in this way. So the spine is a very useful piece of linking infrastructure, but once created, it needs to be updated and maintained over time to continue to be of use. One important consideration during spine maintenance is how do we assemble products from datasets linked to different versions of the spine. It is not desirable to relink every dataset each time the spine is updated. So how do we use the links to a previous version of the spine with the current version? We also need to consider how best to use the new information, which will contain new units on each of the core datasets, as well as updated information. For example, changes of name and changes of address. This new information can lead to better links, but we still need to keep in mind the issue of assembling products across the different spine versions. 4 broad options were considered, ranging from minimal change to spine elements already formed, which is the quickest, easiest process from both a linkage and an assembly point of view, but it has quality implications. We may have updated information that suggests a spine linkage is incorrect, but this option does not allow the flexibility to change the spine elements once formed. At the other end of the spectrum is a complete spine rebuild each time, which is far more time consuming and complicated from the linkage and assembly side, but from the quality perspective, we are creating the best links based on the most up-to-date information. The agreed way forward was to allow selected spine elements to be broken apart and potentially relinked differently while keeping the bulk of the spine the same. It does pose some complexities for linkage and assembly, but not on the same scale as a complete spine rebuild, but allows the flexibility to fix up spine elements as we go. A few other interesting aspects of the spine maintenance process include a graph-based component of selecting spine elements to merge. The way we currently build the spine, as mentioned earlier, was to sequentially link the datasets. Based on this methodology, it is possible that the ordering of the linkage may impact on the resultant linkages. This is not expected to be large, but we have also implemented a technique where we conduct all the pairwise linkages between the core datasets and then use graph methods to resolve these into clusters. Comparisons between these results and our spine show that in some cases the results of this graph method could identify mergers in spine elements that our spine build process was unable to find. We also need to identify the spine elements to break apart and allow to potentially relink differently. This was based on a combination of identifying records with relevant updated information, for example, change of name or address, now being available for records that previously had no address, plus a method we implemented based on the theory for probabilistic linking, where weights are generated based on agreement patterns between the events from the different core datasets contributing to a spine element. This identified a number of spine elements to break, though as expected most relink exactly the same during the spine maintenance process anyway. So, in conclusion, the spine has been created as a foundational linking infrastructure which is a sound basis for extending across time and expanding to include datasets from across a broad range of sectors and jurisdictions. With a planned annual refresh process, the spine will continue to be maintained over time and improved to meet the rapidly growing needs of analysts. The spine maintenance process allows for consistency between spine versions while also allowing the opportunity to fix false links. We are always looking to improve the spine and the spine maintenance process, and a few of the areas of further research include further improvements to the coverage of the spine with the inclusion of additional datasets. Whether we should do a complete spine rebuild process at some point, or if we should move to doing that as part of the standard annual refresh. And also, how often should the graph methods approach be conducted? If there are any questions, they can be submitted via the conference organisers or can be sent to the email address provided. Also listed are some relevant pages on the ABS website with more information. Anyone interested in gaining access to the MATTP data asset can also use the email address provided to make contact with the ABS. Thank you.